Other one is May the 6th. I'm training very hard. Very, very hard. So things are hurting and then, getting a little bit tight here and then there, sore everywhere. But that is all planned because next week is a vacation week. So I won't be able to do any of live stream next week. But I'll still try to keep the streak going on. So, basically there'll be no training next week, right? 0. That was planned, an off week. So this week is going to be hard, I know. And also I don't have full 6 days to train. I'm leaving on Friday, which means I only have 5 days to train, right? So I have 2 more days, tomorrow and the day after tomorrow. So tomorrow I have 1 more volume day in the morning. And on Thursday morning, I'll have to hit the heavyweights. Ideally, I hit the heavyweights plus the front squat, but I doubt it because Thursday I always have the weekly stand-up in the morning. And that's usually not gonna be enough time in the morning. So we'll have to think about how to do it. I mean, I can just train really fast. Yeah, if I train really fast, maybe it's possible. Maybe it's possible, but we'll have to see. All right, let's do it. Find minimum time to reach last room. We have a dungeon, n by m rooms arranged as a grid. 2D array move time of size n by n, where move time I represents the minimum time in seconds when you can start moving to that room. You start from the room 0, 0 and can move to an adjacent room. Moving between adjacent rooms takes exactly 1 second. Return the minimum time to reach room n minus 1. Hold a second. Wait, is n? Oh, it doesn't matter. It doesn't matter. It's just the bottom right. Okay, so start example is 0, 4, 4, 4. I think it's guaranteed 0, 0, 0. Hey, there's no guarantee. There's no guarantee. I don't have to be. Alright, so minimum time required. So I start here at time 0. I cannot move until time 4. Right, but then when I move it, it'll be time 5. And then I come here, it'll be time 6. Okay. Now this one is all 0. Right, all 0 just means you can do whatever you want. So it's going to be like a Manhattan distance, right? So it's just like this. So it'd be 1, 2, 3. The minimum is 3. The last one. The last one is 0, 1, 1, 2. So I wait 1, come here is 2, so come here is 3. Okay. I mean, this is just like a cost, right? It is just a cost. This is basically a cost. So I don't know. We can Dijkstra this, right? We can Dijkstra this, and basically we have the cost, right? And we need to find the minimum cost. Then when we move there and then we increment, and then we see around, and we need to find the minimum cost. Well, hold a second. Not necessarily minimum cost, because yeah, it's fine. It's fine. Like if it's we try minimum cost, right? But it doesn't have to be. It doesn't have to be, because if you already waited enough time, and the remaining is basically they're the same. They don't cost you anything. You can go anyone, and we go whichever one, and then we try, right? We try, and then if it's bad, yeah, I think Dijkstra shall be able to handle this. We just need to code the Dijkstra. All right. So we'll try Dijkstra. 3341. We will use Dijkstra for this. All right. So Dijkstra, I need priority queue, and I also need. I don't need anything else. I just need a priority queue. Okay, so priority queue, and it's a min heap, right? No, I think that's a max heap. It's a max heap. That's fine. What do we put in there? I need the I need the J, and I need. So I have to put. I can't put a pair. Technically, I can put a pair. Right? I put the int and. Right? So I say Q. Right? And then I need to do vector. Oh, I need to also do this. All right, the way I like to do it, m equal to move time dot size, n equal to move time 0. Okay, dot size. And this is going to be the int. Time. Move time is the current time. No. Reach time. Right, reach time is going to be m and vector int n column. Right. What's the default value? Default value should be huge, right? Because we want a minimum, so the default value, well, it's 10 to the 9th. What the hell? Wow, can we do like int max? Right, so we get a max value for every single one. And we'll start by setting the reach time 0, 0 equal to move time 0, 0. Right, so that's that. And q dot push minus move time 0, 0 and 0 and 0. So while q dot empty, all right, q is not empty. Auto element equal to q dot top, q dot pop. Okay, so we have reach time is element 0, but need to take a negative. And always get the smallest out, which way this is the largest. And then actually no. Dot first. Dot second. Dot first. J is element dot second. Dot second. Okay. So now we got this, and we need to look. Push. It's not push. Oh, it is. It is. I just did that one. Shouldn't be this. Should be like this. There we go. All right. So we also need a std vector of std pair int dirs 0 1 0 minus 1 minus 1 0 and 1 0. Okay, that's directions. Okay, so now we have this. Right, we pop it out. Oh, and also the current time. This is the current time. Right, this is the current time. Yeah, current time. Right. Okay. Now we're gonna go through the 4 things that you have 4 directions, and we check if anyone has the minimum, right? And if it is, then we just go there. So we shall say for auto pair of DRRs, right? Di equal to p dot first, dj equal to p dot second. Okay, and if di is logical to 0 and di is smaller than m and dj is logical to 0 and dj is smaller than n. Okay. One more thing, and actually that's not true. We shouldn't even do this. It shouldn't be. It should be ni is I plus this. Nj is j plus this, and then we only handle n. Okay. Now we can say and it's a little bit more complicated. Let's do this. So yeah, this is a good one. Then we can check its time. Right? Because we look for directions, and then we need to check its time. Then we say int current time next time, right, shall equal to it depends on whether move time in I and j, right? If move time in I and j is larger or equal to smaller or equal to current time, then just current time plus 1, right? Otherwise, so you can have to wait until it's full, then you move. So it should be that one plus 1, which is move time in I and j plus 1. Right? So this is the next time. And we say if next time is smaller than reach time in I and j. So that's a good case. Then we say reach time in I and j equals the next time. Yeah, let's just spell it out. Expression result unused. Okay, so next time I set it, and then I need to say q.push. Okay, so the next time, right? And then we put ni and nj into it. Cool, right? So we go this, we blah blah blah, we do, we keep going, and when do we stop? Well, we stop when we hit, right? When we hit the end. We hit the end. So it's going to be here if I is equal to n minus 1, right? And j is equal to n minus 1, right? Then we will break. No, instead of break, I will just return current time, right? Current time. And then this one will get to the end, and then we'll say return -1, which we should never reach here. Yeah, I feel like that's what Dijkstra is. Let's see if it works for the simple test cases. Oh, looks solid. We'll try it. Okay, we got quite a few right, but this one is not right. That's small enough test case. We can really handle this. Oh, I think I know why. I think it's not necessarily the first. So we don't even check this, right? We don't even check this, and then we just return reach time n minus 1 and n minus 1. Well, it'll be a little bit longer, but yeah, but you cannot say the first time you reach is the best. That's still not right. Okay. Okay, it's fine. That's fine. Something is not right. The answer is the same, 58. Well, let's take a look. What was the problem? Expected 39. So are we not respecting this number? Because if we don't respect this number, wait a second. Even if we don't respect this number, this has to wait until 94. This has to wait until 4. This is with 39. Okay, so essentially what we're saying is we don't respect this number. We always start from 0. Right? That's essentially what it says. We always start from 0. Huh. Let me read again. The minimum time in seconds when you can start moving to that room. And then we already start from, so we don't start moving there. All right. So we set it to 0 then. Yep. That's exactly it. We set it to 0. I don't remember. What's the complexity of a Dijkstra? Is that a... Actually, oof. I should know, right? Dijkstra complexity is OMN log MN? Is that what Dijkstra complexity is? Yep. I just took a guess, basically. Yeah, OM and log m, and that's the complexity. Yeah, I think it's pretty much the same. You do have to create, they have the directions, they have, I don't know what these things are. DMV. What is DMV? Don't know what DMV is. This is lambda. Dot dis. Did they create a new struct for this? They did. Should be a struct. Okay, I think there should be a struct. Will make things a lot easier. I'm just using pair, which essentially is the same. Blah blah blah. Continue. I'm gonna do that. Where is the priority queue? Oh, here's the priority queue. Okay, queue and yes. Oh, that's a good one. Maximum distance. This plus one. Yeah, that's essentially the same logic as this, but expressed much better. And then if it's larger than the dist, yes, we do this. And then we go, yep, that's exactly the same. Exactly the same. All right, that will be it. Good. Yeah, Dijkstra, usually we are pretty good with Dijkstra. Done it many times. All right, that will be it for today. I'll see you guys tomorrow. Adios.